Hello, one and all. Bienvenue à tous. If you're tuning in live, thanks for making time for us in your busy day. If you're watching this on YouTube, thanks for stopping by. Whichever way you're joining us, welcome to Post Media's sixth season of Driving into the Future. The name of today's panel is Battery Tech in the Spotlight, and I'm David Booth, senior writer for Driving.ca and your host for today's panel. Electric vehicles are the future, or at least a very big part of it. But to continue making inroads into the mainstream auto market, fast improvements are needed. Better batteries and faster charging, longer range and superior efficiency, and we need to do it all a lot cheaper. In a nutshell, we need more energy dense batteries, more efficient electric motors, and cheaper production so that the EVs of the future can travel further, charge faster, and do it all for a lot less money. It's a hell of a challenge. Lucky for us today, we have four experts who are going to illuminate what the path to better battery electrics might look like. In the next hour, we'll hear about a new battery formulations, a dramatically more efficient electric motor, and how it is all going to be manufactured. To help us understand what lies ahead, I'm joined today by a most august panel of experts. Michael Pope, Associate Professor of Chemical Engineering at the University of Waterloo, Ewan McTurk, consultant battery electrochemist at Plug Life Consulting, Steve Levine, editor of The Electric, and Stefan Ender, co-founder and co-CEO of Deep Drive. Welcome to you all, and thank you so much for joining us today. Before we jump in, let me welcome all our viewers and let them know we will be trying to answer some of your questions that you've submitted. Michael, I'm going to start with you. You're in a process of building Ontario's Battery and Electrochemistry Research Centre. So I'm going to ask you to get us started along this path to enlightenment. We seem to read about new battery breakthroughs every week, but how many of them are real? And can you walk us through what we can expect in terms of new batteries over the next few years and beyond?
Okay, thanks, and thanks for having me on the show. So there's a lot of, I think, nuance in terms of making batteries, right? So there's lots of parts to a battery. There's a cathode, an anode, there's membrane, electrolyte, and all sorts of components. So there can, there's, I get in my news feed all sorts of articles about, this and that, invention, right? And I'm part of that also ecosystem, right? That's we're all sort of working on like a small aspect of that big problem. So I think some of these are going to see, commercialization, but I think what companies and investors are looking for at the moment are sort of like proof that your advancements can actually be scaled up and you can have sort of a good performance in like a large scale prototype. So that's one of the things that our facility our OBEC, we're calling it, is aiming to do is to help to sort of translate some of that new technology into prototypes so that maybe small, medium-sized companies can come and make a prototype and show the improvement, to bigger industry partner.
Thanks very much. Ewan, I've done a bit of research on you, and you seem to be a PhD of all trades, Plug Life Consulting on pretty much everything battery electric. So I'll toss you a bit of a curveball. What exactly are cell-to-body batteries? How do they make EVs more efficient, and are there any downsides?
So cell to body slash pack batteries are an attempt to remove the stuff that stores energy so that you have more stuff that stores energy. In other words, you're improving the efficiency and the lightweighting of the vehicle, bearing in mind that Tesla's bigger battery packs are around about 500 kilograms. This is a weight that we're keen to save. There are numerous evolutions of the cell to body slash pack strategy, but they fundamentally start with the removing of modules, because normally you'll have bite-sized modules. If you look at the likes of a Tesla Model S, the modules are kind of yay size. You could just about carry, it'd be reasonably heavy, but you could carry one. And then these all get stuck together effectively like Lego with bus bars to produce the right system voltage. By removing those modules, you're removing the casing, which means that you're removing dead weight. You're lightweighting the vehicle. Cell to pack takes this a bit further. Well, sorry, that is cell to pack, I should say. Cell to body takes this a bit further by looking at the outer pack casing and going how can we remove some of this as well? So cell to pack, it's quite a broad church. Some efforts actually aren't as revolutionary as you might initially think. You are literally removing the top of the battery box and using the underside of the chassis to double up as the top of the battery box, and basically, securing it to the underside of the vehicle like so. But cell to body, in its most extreme form, is where the cells themselves not only form a rigid structural load-bearing part of the chassis, but potentially can actually become part of the chassis as well, which means you're not only removing the weight of the battery casing, you are in effect removing the weight of what was previously steel or aluminium making up the chassis and replacing that with something that is storing energy to power the vehicle.
Okay, that's really interesting. I'm sure some of our readers or listeners haven't heard of that, but I want to follow up. I read that the Chalmers University is proposing we build a car out of carbon fiber. The carbon fiber also doubles as its battery. So the carbon fiber is the body and it's the battery. That sounds a little fantastical. Can carbon fiber really be used for the anodes? And does this really solve the battery weight problem?
So that Chalmers study is very early days, but it looks quite promising. The energy density, however, is one of the numerous caveats that we need to bring into this. So the carbon fiber battery, to put it into perspective, one half of it is pure carbon fiber. The other half is carbon fiber that's coated with LFP, lithium iron phosphate, which is a low-cost cathode material that's gaining a lot of popularity across the globe just now. It's also cobalt-free and comparatively ethical. A class-leading lithium-ion cell that you would find again in the likes of a Tesla Model 3 or Y is about 250-ish watt-hours per kilogram in terms of its energy density. The Chalmers carbon fiber battery is 30 watt-hours per kilogram, so it's about 8 times less energy dense. But because it's replacing the actual aluminium that's forming the chassis, and is lighter than that aluminium and is stronger than that aluminium, you actually end up with a net benefit. And of course, a chassis is a fairly large component. So if you can get enough capacity in there to power the vehicle, then you are you're in for a very efficient electric vehicle because you're not carrying around up to 500 kilograms of additional weight in the form of a dedicated battery pack. But there are caveats here. The pros, again, ethical materials as described. You even don't need as much copper or aluminium for the current collectors, as we call them, onto which the active material that stores energy is coated. We don't need as much of that with these carbon fiber batteries. The Coulombic efficiency, energy in versus energy out, is pretty close to 100%. The degradation seems to be minimal over 1,000 cycles, which is incredibly respectable. But if we delve more into the paper, there's a couple of things to look at. First of all, the elastic modulus. Now, I'm not a mechanical engineer, so I'm not entirely sure what an elastic modulus is or where I can buy one, but aluminium's is about 70 gigapascals and carbon fibers is slightly more than that, about 76. But once you've cycled these cells, that elastic modulus actually decreased to 60-ish something. So clearly there's a degradation in the structural integrity of the vehicle over time using these batteries. That's something that needs to be worked on. But then again, it's still very strong. It's not that far off aluminium, and you can design that in to the to design the vehicle for you design a vehicle for the end of life, not for the beginning of life, so that it is still safe and capable of doing its job. So you would factor that in. The issues include, however, power density is not great. So it can store some energy, but the speed at which it can deliver that is not great. So in the meantime, they're focusing more on consumer electronics, which are low power drain, than potentially high power electric vehicles. Other considerations are, how would we awkwardly shape batteries in these fairly kind of awkward designs, but keep them roughly the same capacity as each other. Individual cells, I should say, how should we shape them into different parts of the chassis, whether it's the A-pillar or the under tray and what have you? How can we make sure that everything is roughly the same capacity as each other, and then put them together in the right series and parallel configuration to get the system voltage and the capacity that we need to power the vehicle? And arguably the most important, what happens if that vehicle is involved in a crash? Is the vehicle going to be electrically safe for its occupants and for anyone who's been unfortunately hit by it? So there's still quite a lot of work to be done. This is still incredibly early days, but it's a brilliant piece of research, and the team at Chalmers should be incredibly proud of what they've achieved. Whether it would make sense for mass-produced electric vehicles remains to be seen, but it's an interesting stepping stone in the right direction for niche applications and potentially for consumer electronics at the very least.
Thanks very much. Steve, your reporting on the business of actually manufacturing batteries is without equal. Anyone truly interested in who's building what, where, and for how much really needs to read your posts at The Electric. So while Michael and Ewan have been detailing all the amazing things we could have, you've been writing on the problems a lot of startups have been having producing the next generation of batteries. Why don't you walk us through who's having problems, how it affects the industry, and why you think it's happening?
Thanks, Dave. I think probably the most useful way of going at that question is not who's having trouble, but because there are so many players having trouble, but instead who's doing it well. Who's coming out okay. So we did see just a couple of players. We saw both European homegrown battery startup champions either fail or move away from from the work. So we saw Northvolt declare bankruptcy. That's Swedish battery startup, completely failed to make batteries. Discovered a key thing about making EV batteries is it's not like making scrambled eggs. It's not like making toast. It's an art. And Chinese companies, Japanese companies like Panasonic, South Korean like LGES, and Samsung have spent the last 10 or 15 years iterating, right? Figuring out how to, step by step, take out inefficiency, build up the yield, learn how to make these batteries and earn some profit while doing so. Startups like Northvolt and another one, Freyr, which in the last 6 months had so much trouble making batteries that stopped making batteries. It's now a solar company, and 2 days ago announced that they've shifted from their European headquarters to Austin, Texas, and so why have the Western startups had this trouble? It really goes back to to what I've already said, that it's very, very hard scaling up, making nickel-based batteries, NMC, and iron-based batteries, LFP. These are the main two chemistries that are in EVs, and achieving high yield, meaning being able to only waste maybe 1 or 2% or less of your production to defects, and so where are we now? Where are we? The place we are now is that the companies that started out going public in 2020 and 2021, like QuantumScape, SES, Solid Power, I already mentioned Northvolt and Freyr, have all of them given up making batteries themselves and have announced, okay, we're going to provide the secret sauce to someone else, and we hope to persuade one of the big guys to make the batteries for us. The question then becomes, why is it in in the case of the Chinese, why is it in CATL's interest? Why is it in BYD's interest or Panasonic's interest to make these batteries for a competitor or a would-be competitor? So I would say, just to tie this up in a bow, where we are right now is that the Western players completely, entirely reliant on mostly Chinese makers of batteries, some Japanese, and of course the South Koreans. And there's really no sign. There's no sign of anyone having the stuff to be able to break in.
Well, it sounds like while it wows us to hear about new battery chemistries, that's the easy part. The hard part is actually making the darn thing. So thanks very much. Stefan, you and your fellow engineers at Deep Drive have developed a new, more efficient type of electric motor. We're talking about some serious improvement in range here, all without needing bigger batteries. Why don't you tell us what it is, how it works, and most of all, small words, please, and no vector analysis. Some of us had a very hard time with third-year electromagnetics.
Yeah, sure. I'm very happy to be here and explain this. So basically what we've developed at Deep Drive is a dual rotor electric machine in a radial flux topology. What this means is that we have the stator in the middle, and we have a rotor on the inner side and on the outer side. And those two rotors are creating two air gaps in the electric motor. You will also see this in the animation now, with the two rotors, inner and outer runner, and the stator directly in the middle. And this is now creating two air gaps, increasing the material utilization, because we can use the full potential of the material for the electromagnetic performance. And this is really increasing the efficiency, but especially, and this is also the question we often get, is, okay, an electric motor is already quite efficient, which is the case only in the best point in the operating map. And where we are really improving with this dual rotor topology is bringing the efficiency up in the whole area of operating points, because often you're driving at low torque, low speed, slowly in city traffic, sometimes faster on the road, but not doing kickdowns all the time. And especially in all this real driving operating points, we are getting much more efficient. And this is what's creating this 20% range increase without touching the battery. And this is also a quite big focus, because when talking about range, the first view is always the battery. But in the end, it's about optimizing the whole system. And we are getting 20% just out of the motor and power electronics, creating new possibilities for the whole car.
The one thing I got out of your research paper and also the animation is that one of the reasons why it's more efficient is because you have a rotor on the outside as well as the inside, you're not wasting any electromagnetic flux. Normally there's just the housing out there, and any flux in the outer direction is wasted. And is that why you get a
Exactly, yeah. This brings it to the point, basically. And this is bringing up the material utilization and increasing efficiency.
Okay, super. Michael, we're back to you. The battery chemistry of the day is solid state. Can you tell us what that is? What exactly is solid in a solid state battery? How does that help a battery become more efficient? And what can we expect from this new generation of batteries?
Okay, so to understand this, I just want to explain, I guess, how a normal lithium-ion battery works. So we have an electrolyte, which allows lithium ions to move back and forth. And this electrolyte in the typical lithium-ion battery you have in a current EV would be made using like an organic electrolyte with a lithium salt dissolved inside. So this is like an organic solvent system. So that's going to be, most organic solvents are flammable. So if there is like a thermal runaway, like that flammability sort of makes the lithium ion battery more dangerous, right? So To try to avoid that sort of situation, researchers are developing solid state electrolytes. So these can be polymers with lithium salt dissolved. There's ceramic materials that contain lithium, or there's these sulfides, these sort of ductile sulfide-based solids that are quite have a quite amazing ionic conductivity. So these solid materials can then they're not typically flammable. There might be, I think it's early days, so there may be other concerns that we haven't found yet, but they at least remove the flammability aspect from the battery safety concern. So that's the big, I guess, draw, I guess, for there's several draws towards solid state. So if you can make the whole battery solid state, you improve safety. So maybe you can then actually reduce some of the safety mechanisms that are currently in EVs. So maybe you can reduce the amount of steel needed to reinforce, there's like usually, I think, a thick plate between the battery and the passenger, right, to prevent any sort of failure. So you could make that thinner, right? So you can, maybe think about lightweighting, right, reducing some of the maybe weight of the coolant or battery management system, right? So there's sort of ancillary benefits to moving to such a solid state system. I think something else which is kind of pretty interesting is that I think manufacturing these batteries can also get easier with solid state on some aspects. So one of the major, I guess, things that liquid electrolytes need to do is every battery that one of these big players makes, whether it be LG Chem or Samsung or whoever, every battery needs to be worked in essentially at the factory. So they have you can imagine there's billions of batteries coming off the line, and they need to plug each one in and sort of like charge and discharge them. And then they sometimes will fill them with a bit more electrolyte and do it again, right? And this is quite an arduous task. So you can imagine if you're able to mix the solid state everything together, right? You don't have to do the sort of liquid sort of work in cycling, right? So there's some aspects like that which are also sort of promising. But of course, we haven't seen this quite commercialized. I think Steve mentioned a couple big players in the space, that are trying to commercialize solid state, and there's been quite, at least from the news articles I read, quite big advancements in that area. But putting these things together, you can imagine if you take two solids and try to contact them together, it's very challenging. You have to apply large amounts of pressure. You can imagine if there's volume expansion of the battery material during cycling, you're going to have sort of cracking or failure, mechanical failure, right? So actually getting everything bonded nicely into good contact is like a huge issue. So currently researchers are applying huge they apply a huge pressure to sort of first form these, and then they apply a huge stack pressure to hold everything together. And that's not really fitting right now with how pouches and prismatic cells are made, and so we need to reduce like how much pressure is necessary for these sort of systems to work before I think we'll see them sort of deployed commercially.
Just one quick follow-up. Is the fact that the solid electrolyte is more robust, is that what allows them to be charged faster? In that it, basically the heat is always the limiting factor to charging because they're more robust. Does that allow more heat to be applied?
Yeah, so there can be because I guess one of the concerns when you heat up a battery is that you'll start evolving some oxygen, and that can start combustion with the organic electrolyte, right? So with the solid state, again, you don't need to do that. So you can heat the battery a bit hotter than you can with current lithium-ion systems. But like you mentioned, the mechanical properties, right? So if you have a liquid electrolyte, one of the issues, if you have, like, for example, fast charging, you might get lithium dendrites forming, and these can cause this thermal runaway issue as well. So what happens with the solid state electrolyte is you may be able to charge faster without worrying about lithium essentially penetrating through the solid material. Although it's been shown that through grain boundaries and some defects in these solid systems that you can still get sort of lithium dendrite growth, but at least it can maybe be, at least you can improve the rate to some extent before you hit that failure mechanism.
Thanks very much. Ewan, so we've just talked a bit about the future, and I love hearing about cutting edge chemistry as much as the next guy, but we also need better, cheaper batteries right now. Lately, I've been reading about something called LMFP, which is supposed to be the best of both worlds of lithium iron phosphate and nickel manganese cobalt batteries, which we produce here. Can you tell me how it differs from the lithium iron phosphate and what the benefits might be? And do you know who the leaders might be in producing it?
So LMFP is, as you said, it's an evolution of lithium iron phosphate. You're substituting some of the iron for manganese, typically about 60% of the iron gets substituted for manganese. So what happens there is because that well, if you look at manganese, it's typically used in NMC cells, and that cathode material has a particularly high potential versus lithium. So the voltage of a cell is the potential difference in potential between the cathode, the positive electrode, whether it's NMC or LFP, and the negative electrode, which is typically made of graphite. So the bigger you can make that difference, the higher the voltage will be and the more energy it can contain. Lithium iron phosphate has numerous advantages that I won't bore you with just now because of time constraints, but the downside is that it's less energy dense, and that is because its potential versus lithium is lower. So you've reduced the overall cell voltage. The LMFP evolution increases the overall cell voltage by increasing the cathode potential to close to that of NMC. And that means that you can achieve the similar energy densities, not that far off of NMC, using comparatively cheap, abundant, ethical materials, which should, in theory, be safer as well. Although it's worth pointing out that even the most volatile of lithium-ion chemistries in electric vehicles are at most 20 times, or sorry, at least 20 times less likely to catch fire than an internal combustion engine. So we're talking taking something that's already incredibly safe and making it even more substantially safe. But yeah, you're talking, as I say, vastly reduced costs, vastly improved ethics as well. And because you've increased the voltage, you need less active material to reach the same amount of energy, which means smaller, lighter, cheaper battery packs, which even give LFP a run for their money. In terms of who's going to be the market leaders on this, of course, China is going to have something to say about that. They've already put export restrictions on powders of LFP and LMFP because they know that Europe and North America are both very interested in utilizing these chemistries because of because of LMFP's particular advantages in cost and ethics and energy density versus LFP. But that said, there are some interesting companies in Europe and in North America that are developing LMFP, and perhaps one of the market leaders in that regard is Integrals Power from the UK. That's developed a bottom-up approach to producing LMFP rather than taking bulk precursor powder materials and kind of milling them into what would be the powder that would be applied to the electrodes in a lithium-ion cell. They're basically starting from the atom and building them up a bit like Lego, to use a Lego analogy for the second time today. And they're actually using a greater amount of manganese, about 80% manganese rather than 60% than many of their competitors. But they're quite bullish about the performance and longevity of what they've produced. And they currently source their materials from Europe and from North America. So that circumvents the supply chain disruption that we might see with Chinese raw material export restrictions, which is good news for Canadian buyers of LMFP EVs.
Thanks very much. Thanks very much. Steve, continuing with the actual building of batteries, it's well known that Chinese manufacturers are having no problem scaling up production. Their dominance is pretty much incredible. How much of the battery business do they now control? Why are they so efficient about it? And more importantly, how much cheaper can they build a battery than our Western producers?
Yeah. This is so. Two battery companies, CATL and BYD, make 54%, around 54% of the EV batteries in the world. It's two companies. CATL alone, 37%. So they've got the market. And then when you add up everyone, the top 10 producers. I'm going on memory right now, but I think there are 2 South Korean, basically 7 or 8 out of the top 10 are Chinese. So that's where we're getting virtually all of the LFP comes from China. You've mentioned and Ewan talked about LMFP. CATL has got a formula mixing LFP and NMC together because one of the main problems with LMFP is you're not getting as many cycles out of the battery. You've got to have 1,000 cycles, to be that's kind of the standard in EVs. 300 let's say 260, right? If it's an LFP battery, and then 1,000 cycles, you've got a 250,000 mile car. So that's pretty good. But if you put manganese into the LFP, you lose a lot of the cycles. I haven't figured out how to get that many cycles out of it. But by mixing CATL, mixing NMC into the LFP, you get the upside of the LFP, which is the low cost, and the upside of the NMC, which you get the cycles. You get higher energy density. So, the question was, how have they done this? It's not just that CATL and BYD have been doing it longer. They've been more artful, more skillful at it. The cell to pack, cell to body was mentioned in the very beginning of this conversation. This was invented in China by BYD and by CATL in 2018 and 2019. They mastered this, and this increases the energy. This is what made LFP a factor in global EVs. They were able to take low density LFP and increase the energy density, increase the number of miles you get in a lifetime, in a cycle, from an LFP propelled car to reasonable, 250 miles, even 300 miles. And the main way that they did that is cell to pack, right? Removing modules, removing that unnecessary packing. You spoke about solid state. I'm highly skeptical that solid state ends up in EVs anytime soon. We've got a bunch of companies boasting, claiming that this is going to happen in 2028. Maybe, but they're not using. The whole reason for using solid state is to get lithium metal into batteries safely and get that energy density. They don't say what the what the anode is, and the suspicion is it's a silicon anode. You don't get the upside. It's sort of gimmicky, but in any case, the long and short of it is that the Chinese have eclipsed the South Koreans and the Japanese, and of course the Americans, both in manufacturing and in being state of the art in terms of these next gen batteries.
Well, I certainly hadn't heard of the LFP NMC thing, and I pride myself at least as a journalist in keeping up with that stuff. Okay, Stefan, back to electric motors. What are some of the other benefits of your dual rotor radial flux design? Does all this efficiency cost more? How can it be used? Talk about where you go from the design stage to the production stage. Can we do it economically?
Yeah, that's a great thing about our technology, the deep drive dual rotor, is that we get this very, very high efficient at a very good cost level. And the main advantage here is this dual rotor is on the one hand side increasing efficiency, but it's also increasing torque density. So what we can now do and what we also focus on is keeping the torque at the same level, but realizing this with less material. So this means we need less copper, less iron, less magnets in case we have a PSM machine for the same torque output at this higher efficiency. And this is in the end ending up just purely looking at the bill of material with a quite significant advantage in cost already. And on top of this, we have built this machine for being it's really made for large scale. So this means all production processes from the very beginning are designed for large scale production. So compared to the state of the art electric machines, we are not doing anything fancy. We are just doing the processes as they are done today. But we just kick out some of the process steps. So in the rotor, in the stator, for example, we reduce the amount of process steps by 50% to produce the motor, and the 50% remaining processes are pretty well known in the industry today, especially for large scale electric motors.
Okay, so with the dual rotor, now you have two rotors, one outside the other. Does that make the motor physically bigger? How does it used? Is it small enough to be used on an axle or even smaller than that? Or is it one big motor mounted centrally that powers all four wheels?
So basically, it's pretty scalable in size, also in diameter. And we always have this advantage of torque density compared to other technologies. But for sure, for powering an electric car, you always want a certain diameter because there's a best point when it comes to cost and diameter, because diameter is always good for an electric motor. So there's some scalability, but usually we go down to sizes in diameter that exactly as you mentioned really fit to electric e-axles. So we fit into all the packages today of electric cars for central drive. So this means the 3-in-1 drive units that are in the center of the car. So this is where our technology fits pretty well, also when it comes to diameter. But we also have a second product line, which is in-wheel motors, where we can also integrate the motor directly in the wheel. Then going for larger diameters because you have the space in the wheel, and then powering the vehicles with the motor really integrated at the wheel hub in the wheels.
Wow, so motors built right into the wheels. Oh boy, the future is interesting. Michael, one of the most interesting formulations mentioned in the creation of OBEC is metal air. What the heck is that? And is it more energy dense? And if it is, why so?
Yeah, so good question. So yeah, so I guess like I can start by try to explain. I guess everybody's seen corrosion to some extent, right? So if you probably have seen a rusty car, I'm assuming the viewers probably, hopefully not too much these days, but an old rusty car, right? So probably you know that oxygen from the air, right, can react essentially on metal surfaces, and they can cause either oxides to grow or dissolve essentially away, right? So this causes holes in our steel things and whatnot. So a metal air battery is really sort of leveraging that, but it's like separating the two processes. So it's trying to use oxygen from the air to essentially as one of the half cell reactions driving the battery, and then the metal is on the other part that's essentially being you can sort of reversibly oxidize and you can strip and plate it essentially. So this is like you can do this with for example with steel, right? So like a direct sort of analogy to the corrosion. And I know there's some news articles a couple of years ago. There's I think a startup out of Yatming Chang's group at MIT that's developing these sort of grid storage iron sort of rust batteries, right? So if you can reversibly sort of control the rust formation process, right, you can sort of store energy. There's a couple other players like that are working on zinc air, right? So zinc is even cheaper than iron, and so it's used often as a sacrificial anode actually when you know, for galvanizing steel and things, right? So you actually do that because the zinc preferentially oxidizes compared to the iron. So zinc is pretty cheap, and so people are also thinking about how to incorporate that, and there's companies like eZinc in Mississauga is one of the Canadian players in the space that's also focused on grid storage, just because these systems are a little bit bulky, and there's still a lot of problems to be had. So problems to be solved, I guess. So you know, one of the main issues I think is just that the metal that you're using, you know, we have to worry actually about the corrosion of that metal in the battery itself. So we try to separate like the two processes, but it's never going to be perfect, right? So the zinc will eventually, you know, start to oxidize, or in the electrolyte, it can start to, for example, liberate hydrogen because it can react with sort of water. So there's a lot of stability issues like surrounding metal air batteries, and you know, the other sort of issue is that even though, so you mentioned about the energy density. So a lot of the reports on energy density are super high because they include the capacity per mass of just the metal. So when you have a battery, we usually have to include the mass of both the cathode and the anode, right? But in the metal air battery, you can just sort of include the mass of the anode, and that a little bit, so that makes a big number when you divide by the smaller number, right? but in fact, like that's a bit cheating because you always have to have the cathode, which is usually a carbon with some catalyst that can support the oxygen reduction reaction that you need to drive the other process in the battery. So it's not that you can't, like you can avoid using an active material because you can just pump air in, right, to the battery, which is great, but you still have to have the infrastructure in the cathode to actually do the chemistry. So that adds weight, right? So and because you need that infrastructure, and it needs to be open to air, you have to worry about what happens when, you know, things evaporate. Somehow the liquid needs to stay in this porous material and not flood. So there's problems with flooding. It's kind of like a fuel cell, right? There's a lot of sort of what they say triple phase boundary. You need air to contact the catalyst, to contact the electrolyte, to contact the solid material, and getting that balance and having it be stable is really an issue. So maybe one day we can think about these for EVs, but I think you know, lithium air is like probably that's the best, obviously, because lithium is going to be the most energy dense, but it's going to be the most challenging to make because it's going to be really air reactive, right? There's all sorts of even more advanced issues with lithium air compared to iron or zinc, which people are sort of tackling, at least for like sort of more cumbersome grid scale systems. But maybe one day we'll see them in EVs, but I think it's far into the future.
If I'm understanding it right, it sounds like one of the advantages that it shares with an ICE car is you don't have to carry all your fuel around with you. Like gas cars carry the gasoline in the engine, in the gas tank, but they bring in like 14.7 pounds of air for every pound of gas they use. And it sounds like these things save some of the weight of the battery by taking air out of the system. Have I got that anywhere?
Yeah. So you can theoretically pump air in. You could, you know, blow compressed air, like have a compressor, I guess, that pumps the air in, but you have to worry about contaminating sort of things in the air, right? So usually with batteries, we work with very ultra high purity things, and so you know, you probably want to use a purified oxygen tank or something like that as the air.
Oh,
right?
okay.
Make it more stable, but
Okay. So,
you know,
so it's not quite as efficient as I thought it might be. Okay.
yeah, but maybe in the future, like the dream is you could just pump air in, and then you wouldn't have to have that mass, right, or that weight.
Okay. Ewan, if we're going to use all these new battery chemistries optimally, we're going to need to charge faster. Here in Canada, the top DC fast chargers currently used are limited to 350 kilowatts. I've heard of 500 kilowatt versions in other more advanced infrastructures, but how much faster can we go? How much further can we go in our race to faster charging? And are there other ways to shorten our time at the stations?
So the charge power that we need to consider, it's all relative. It depends on the size of the battery pack and what C rate you're charging that at. So the power being delivered to it over the capacity in kilowatt hours of that battery pack. So we're starting to see MCS, the megawatt charging system, being developed for electric trucks, articulated big rigs, and so on. Particularly across Europe at the moment, that, as the name suggests, goes up to a megawatt. You're not going to see that being fitted to passenger cars anytime soon. And the reason is that their batteries are so much smaller. You know, they're typically 100 kilowatt hours maximum, nearer 60 to 75-ish kilowatt hours average. So, you know, that would fry most typical chemistries today if you were to apply a megawatt to them. But 350 kilowatts is actually a surprisingly good charge speed if we can maximize the utilization of that. Because at the moment, most EVs that can charge incredibly quickly, like Teslas, for example, Tesla's a particularly good example of this. The charge power starts off incredibly high and then decreases linearly. Some of them will sustain a higher charging power for longer, but they do start ramping down. That's more like a Hyundai Ioniq 5 that I did a little mimicking of there. But if we can sustain that high charge power for longer, then that means your 350 kilowatts is being realized for much longer in that charging session. And we can start to get to sub 15 minute, sub 10 minute charging times quite readily. There are some interesting chemistries that allow that to happen. For example, Niobolt, which is a niobium tungsten oxide based cell that's being developed in the UK. They fitted I think it was a 35 kilowatt hour battery pack. So I know that that's hashtag so 2015 in terms of capacity, but they fitted it to a small lightweight sports car, took it to a 350 kilowatt charger and charged it in under 5 minutes, because this particular chemistry could just sustain lithium ions flowing in and out of it so readily without getting hot. But in terms of the more kind of conventional chemistries we have today, there's an interesting company called Breathe Battery Technologies, which is able to look at very subtle differences in voltage and temperature data coming from cells within a battery pack. And they're able to relate that to phase changes, degradation mechanisms, various things that are going on inside the black box that is a lithium-ion cell. So they know that they can actually be far less conservative with the charging power limits that we apply when we are fast charging or quick charging lithium-ion cells today to avoid those degradation mechanisms happening, because they can actually monitor that far more effectively. And this is being used by Volvo. They're using Breathe Battery Technologies algorithms for their battery management system. And they can basically take the same, pretty much fundamentally the same battery pack and cell chemistry and charge it 30% faster, because this algorithm is able to react to what the cells are very subtly telling it. And that means that we can increase charging power, we can throttle it back or pause for a couple of seconds to let the cell kind of catch up with what's going on inside it in terms of the kinetics, where the lithium ion concentration's at and so on, and then go back to it. Honda similarly is looking at a company called Sonocharge, I believe. I've got it written down here because I'm cheating. Sonocharge, yeah, there we go. So that's all to do with using, I think it was ultrasound actually, to pulse lithium ion cells in a way that helps those lithium ions to get to where they need to be faster. And that again will greatly improve charging speeds, reduce charging times using conventional chemistries. The final thing that we can do is we can be clever about the way that we structure the actual electrode material themselves, rather than just having a flat metal current collector that we then slap some slurry to fairly haphazardly in the grand scheme of things. We can start doing 3D nanostructuring of it so that the lithium ions have a much greater surface area to get in and out. And that's part of how we'll be able to achieve faster charging times, but that's barely scratching the tip of the iceberg of where things are going. The other thing, just to finish this because I'm aware that we're running short on time, you can cheat by swapping batteries. This is done in China, where a lot of people don't have off-street parking. It was tried in Europe and it wasn't successful because many of us have driveways, and we were worried about having a clunker of a battery swapped in, having had our pristine one removed. We now know that EV batteries last a lot longer than we expect. But that said, most of us have driveways, so we're not that bothered. But For very large HGVs, heavy goods vehicles, and so on that are doing very, very long distances, there's a company in Australia called Janus that retrofits their road trains, their massive big rigs, to have 2 large swappable battery packs in the tractor unit that can be swapped out with forklifts in about 5 minutes. The driver would need to take a taco break at that point anyway. That would be about 45 minutes. So that means that they can traverse entire continents without necessarily needing high power charging infrastructure, just as long as you have a fresh set of batteries ready to swap in.
Okay, thank you very much. I didn't know about those battery swapping stations for trucks. Heard of them for cars. Steve, I'm going to put you on the spot a little bit. We've talked about how Chinese battery manufacturers are ahead of us and produce things more cost effectively. But on the other hand, we know that they pay less wages. They don't have the environmental regulations that we might have. The reason I bring that up is President Trump, unlike President Biden, has said that he will bring back, he will allow Chinese battery manufacturers into the States. If they come here, they'll have to pay union wages, they'll have to source arm minerals, and they'll have to adhere to our standards. Will they still be more cost effective than us? And by how much do you think? And Stephen, we've only got about 9 minutes left, so about 3 or 4 minutes, if you don't mind.
Yeah. So when you read back to the same chapter of U.S. Car dominance being threatened, it's in the 1980s and the 1990s with Japan. And when the Detroit and also the European car makers were able to stand on their own 2 feet and compete with Toyota, Honda, Nissan, and so on, the way they did it was invited the Japanese car makers to make their cars in the U.S. And elsewhere. And what happened was that Western car makers learned how to make cars more efficiently with greater yield from the Japanese. And so this is why inviting the Chinese into CATL, BYD, and so on to do their business in the West is really the smart thing to do. And it's not really a cost issue. I mean, the cost is an issue, of course, for the factors that you raised. CATL is not going to be able to make LFP for $35 per kilowatt hour, which is what they're selling their stationary storage batteries for in China right now, in this very brutal cost war that's going on there. They'll have the same costs that everyone else has, but they can make the batteries at scale. Their yield will be very high. It's not just the costs. Western battery makers have utterly failed just to make the batteries. It's not an issue of cost. It's not an issue just of cost. So we do need to invite them. I think that is going to happen. And over the next 2 or so years, right? I mean, there's going to be a lot of huffing and puffing between Xi Jinping and Trump. Maybe for the next year, a lot of threats, but then they'll get down to horse trading, and I do think we're going to have this happen, and it will be the best thing possible for Volkswagen, for Ford, for GM, for that to happen.
Well, God, the first optimistic thing I've heard about battery manufacturing in North America for quite some time. Thank you very much. Stefan, in the last question you could make, you mentioned that you could build your new motors so they fit in the wheels. They're basically a hub motor. Can you explain to the viewers what a hub motor is and how it works, and what are the benefits, more importantly, of having the motor built into the wheel, and where the heck do the brakes go?
Yeah, happy to do this. So basically for the hub motor, what you're doing is that you're building the motor directly into the wheels. So they are directly mounted to the wheel hub. So this means for the rest, everything stays same. So rim and tires, everything stays same for the end customer, but the motor is really integrated into the wheel. And with our technology, we are really the first one who can manage this at a very attractive price position. Having this high efficiency and especially the producibility, so to really make an adaptation in the mass market in passenger vehicles. What's the main motivation for this? The main motivation is basically the thing that you mentioned at the very beginning. So electric cars have to get cheaper. And we have to close cost gap between today's combustion cars and electric cars. And we see the hub motor as one really relevant contributor to this. Because with the hub motor in our technology, on the one hand side, you gain this 20% range. Or same range with 20% less battery. At the same time, you're getting this whole drive unit from the middle of the car out into the wheels. So this is creating space in the car, which can again be used for additional batteries. So we see as an enabler for also other cell chemistry, because now you have more efficiency of the whole powertrain, and at the same time more space for battery. And this is allowing other cell chemistries achieving ranges that are okay for the end customer, and having the biggest benefit when it comes to overall cost structure of an electric car. That's the main benefit we are seeing with the electric hub motors. And the second question was about the brake. So for the brake, we as Deep Drive have a partnership with Continental as the market leader in brakes for automotive today. And what we are doing is really integrating the brake into the motor, especially working with drum brakes for rear axles, but also other options with disc brakes are currently under development.
So, and I just have a second for this, but basically, I always thought that hub motors would be, positioned more for supercars because of torque vectoring and their power needs. But what you're saying is it actually makes sense even all the way down to, cheaper cars, family sedans and stuff like that.
Exactly. And this is also where we have our focus, is exactly those kind of vehicles. Because of these two advantages. So really bringing the cost structure down, creating the space for the car.
Okay, so guys, we have about one. You know what? I'm going to get to maybe two reader questions. We'll have to have 30-second answers. Brian asked the question I think most of us have about EV. While battery weight and range development will increase usability, will recharge times ever get close to gas tank fills with an infrastructure to be as inconvenient as ICEs? You sort of touched on this. Can you give us 30 seconds on that?
Yeah, if you're coming from a position of only having ever driven a gas car and never an EV, speaking as an EV veteran, this is controversial. We don't necessarily need those charge times to mimic those of gas vehicles. Already, an electric vehicle, a modern electric vehicle, can recharge within the average dwell time at a UK motorway service station. And when you turn up at that service station, you plug in, go into the service station for a whiz and a sandwich, and come back to a car that's ready to go, rather than having to then go and join the queue for gas, stand with the car whilst it's filling up with gas, pay for the gas, and then go on your way again. And actually, the slowest form of charging, you're at home on a wall box, is also the fastest form of charging, because whilst the car's sitting there doing nothing and you were going to go to sleep and then get up to go to work the next day, the car is actually doing something. It's charging up, so it's got a full battery for you in the morning. I'll stop there.
Well, guess what, guys? You know what? I thought I might get into one more question. There were about 60 questions while we were coming in, while we were discussing this. So somebody was interested in what we were saying. That all being said, I want to thank you all, Steve, Stefan, Michael, Ewan. You made this very, very interesting. Maybe, if a few people out there understand not only what the future looks like, but some of the difficulties that will happen before we get there, but also, as Steve told us, the possibilities, the optimism that if some of these manufacturers come to North America, it will actually benefit us all. So thank you very much, one and all. I thank all the people that listen to us. Understand that I saw all your questions. I'm going to try to answer them personally, or maybe I'll put it in a column. Either way, thank you. You were listened to. You will get an answer to your question. That all being said, I want to also thank Toyota for allowing this dialogue. They're our sponsors. And all that being said, I'm David Booth for Driving.ca, and we're out. Thank you very much for attending.